All right, well, it's 11 o'clock. We will go ahead and get started. You'll notice that we're missing our physics army. We'll expect a couple others to potentially trickle in as well. So the goal for today is to talk a little bit more about regression and machine learning, specifically something called elastic net regression, some sub-techniques related to that, and when you might use it. Toward the end of class, we'll do a little review activity to start getting ready for next week's midterm. So the midterm in this class is going to be a week from today, and we'll cover sections 1 through 7. So the very beginning up through where we end class today. Questions at this point about the midterm? Yeah?
What's the format?
That is a good question. I don't know. I'm working on it. Hopefully, I will have a better answer for you about the format on Tuesday.
It's going to be like pen and paper, right?
It will be pen and paper. As of right now, there actually is a sizable amount of true-false.
Really?
Yes.
Wow.
We'll see how much of it stays. Other questions?
How much of the test will be designing an algorithm that can evaluate true false questions?
None, but if you would like to design an algorithm that can answer true-false questions, feel free. I did have a professor in graduate real analysis write a true-false exam where all of the statements were true, which was terrible. So I won't do that. They won't all be false either.
Boy,
Good catch, boys.
That would be good.
That would be terrible. Any other questions?
Is there going to be Minkowski stuff?
Maybe.
Okay.
Yeah.
Are we going to have, like I said, review questions or something to that effect?
Yes, but you will build them. So there will be a set of review questions. I'm going to have you guys create those instead of me. Okay. So let's jump back into regression and kind of review where we left off on Tuesday, because a lot of what we did with this section was really just introducing the concepts of why you might choose something other than basic linear regression. So for example, we showed that least squares regression, and we discussed how it works well in some cases. The cases where regression works well are kind of the pie in the sky cases. So if the relationship between the output variable y and the inputs x's are approximately linear, then regression works well. If n is much larger than p, so that double greater than sign reads as much larger. So if we have many more observations than we have parameters in the model, we can come up with a nice stable estimate. However, if n is only a little bigger than p, there's a lot of variation in how the model fits. If n is less than p, so if we have fewer observations than we have parameters, we actually cannot fit the least squares regression model. So in that case, we're kind of SOL. We can't really fit it. So a solution might be to use what are called shrinkage estimates. So artificially force those regression constraints, those betas, down closer to 0. When we do this, we make a sacrifice. So we give up some of the accuracy in our regression model. Those estimates of the regression coefficients beta will be biased because we've forced them downward to be biased. However, that often leads to lower variance. In general, in statistics and machine learning, there's always going to be a trade-off. Methods that are unbiased might have higher variance than methods that are biased, but with a little bit lower variability. So which do we want? Do we want something with lower bias or lower variance? Questions so far? Okay. We also talked about some model evaluation criterion. So we spelled out 3 that we'll use to compare regression models: MSE, mean square error; MAE, mean absolute error. We also might look at the root mean square error. There's a 4th that I left off here, R squared, or adjusted R squared. So the correlation squared between the predicted output and the actual output in the testing data. We also talked about our data set. So as a little refresher, we're going to work with a data set that is predicting air quality, so hourly CO2 measurements, based on sensor data from a large Italian city, probably Milan. There were a lot of NAs. It's possible that these NAs were systematic. So many of the variables had 480 observations missing. Maybe those 480 observations missing represented a time where the system or the sensor was failing, for example. So we took out those NAs. We also took out some weird extra columns. So here's the data. We're going to create our testing and training data set. Here I'll use a 70-30 split. So I've got train representing my training data, test representing my testing data. And I'll go ahead and just fit a basic linear regression model. So I'll use method GLM. This indicates the generalized linear model. This is a much broader model than just overall regression, but GLM implements regression, or implements linear regression unless you tell it otherwise. When we do this, we get an error. The error has to do with rank deficiency. So if I open this code and run it, I'm going to get that same rank error that I've been getting many times in the past. Why do you think that rank deficiency is coming back to us? We saw it happen a lot with categorical data. Tended to happen when we didn't have enough categories. Why would it be happening in regression? I'll run the code. We'll run everything before. We'll add caret. I wonder why that's not finding itself. There we go. So it takes a while to fit this model. And we get this rank deficient fit throughout. Any of these variables look like they might be causing that. Remember, we tend to see this happen when we have variables that are categorical and not a lot of observations within a category. Josh?
I've seen something about the correlation between variables causing this as well.
Mm-hmm.
And so when you have very strongly correlated, two variables strongly correlated together, is that potentially what's happening here?
That could be what's happening. So if we have two variables that are strongly correlated, we have issues with rank deficient fit. One of the other problems here might be how date and time is stored. Especially if we look at the complete observations, it might be that we just don't have enough observations at a particular date and time to really account for that. Especially if we consider that this is air quality complete. If we consider how these are stored or what class these take on, and if we spell complete correctly, time is stored as a factor. Date is also stored as a factor. So we're looking for repetitions of those categorical variables, and we're just not seeing them. So that's part of the reason why we might be suffering, or why we are suffering from rank deficiency here as well. Now, this again happens when the matrix of input variables is not of full rank. In other words, there aren't enough observations available to fit the model. If input variables are near linear combinations, like Josh said, if they're strongly correlated, this is a problem. If we don't have enough repetitions of a certain category, it's also a problem. So instead, what we could do is maybe remove date and time from the model. We have 14 input variables, 580 samples in the training data. Root MSE is about 0.23. Mean absolute error is about 0.7. Remember, these are unit dependent, so alone mean square error and mean absolute error can't really tell us much. We'll need to compare them to something else. R squared, however, the squared correlation, this is a unitless measure. So the higher the R squared is, the better the model's doing. Looks like R squared is 0.97. So that's pretty high. What's the highest R squared could be? 1. Yep, because it's the squared correlation. Now, let's do this on the test data as well and make some suggestions or look at how well we're doing on the test data. So here I'm taking my predictions, adding them to the test data. Caret has built-in functions to calculate R squared, mean square error, and MSE. So R2 calculates R squared. Also pretty high on the testing data, which is a good sign. Mean square error, comparable on the testing compared to the training data, good sign. Mean absolute error, again, comparable on the testing data. So, good sign so far. So, it doesn't look like we're doing too terribly with these. Remember, we're using these metrics to decide between multiple regression models. So, alone, they can't really tell us much. But I do want to talk about some more interesting models that we could maybe use. So we'll focus on ridge, lasso, and elastic net regression today. We'll likely come back to principal components regression after the midterm. So regularization is going to be the name of the game here. And what regularization does is add an additional regulation constraint on these parameter estimates, specifically on the betas. So we're going to force these betas down towards 0. One thing that definitely should remember, we're forcing bias on these parameter estimates, so we wouldn't want to use this if we need to do inference. So if we're interested in how, say, a certain particulate matter in the air directly affects hourly CO2, and we want to understand that beta coefficient, we shouldn't use regularization. But if all we want to do is try to predict pollution at a specific time, then this works pretty well. All right, so here are the two major methods for regularization. The first is something called ridge regression. The idea here is that we'll place an additional restriction on the sum of the squared coefficients. So in least squares regression, we choose these parameters, beta, to restrict or to optimize two quantities. So least squares finds a solution by setting the sum of the errors to 0 and minimizing the sum of the squared error terms. We refer to this in statistics as RSS, or the residual sum of squares. Since those error terms are often referred to as the residuals. So that's where that RSS term comes from. Now, the estimated ridge coefficients actually minimize something a little bit different. We take the usual least squares constraint and we add an additional restriction to it. We minimize this quantity instead, the reduced sum of squares plus some lambda times the sum of the squared coefficients. This lambda is a tuning parameter. This is something that we'll try to optimize when we fit the ridge model. In practice, typically this lambda is fairly small. Most of the time less than 0, much of the time less than 0.5 as well. This lambda, remember, is going to be directly proportional to the magnitude of these coefficients. So if these coefficients tend to be pretty small, then we might be in a situation where we would expect a larger lambda might be a better choice. if these coefficients are, say, 2 or 5 or 10, these sums of the squared betas are going to be pretty big. So it'll take a small lambda to optimize this. So seeing lambda of, say, 0.05 being the best lambda doesn't necessarily mean that the ridge model isn't changing much. It just means that perhaps these squared betas were pretty big to begin with. Questions so far? Yeah.
Just to clarify, you said lambda less than 0. Is that correct? Lambda can be less than 0 because on the board.
No, sorry, lambda less than 1.
Okay.
Yep, sorry about that. Lambda should be less than 1 a lot of the time in practice.
Okay. But it's not bounded by 1. It could be greater than 1 if it makes sense for some reason.
Absolutely. Yep, lambda can be greater than 1. For example, somewhere where you might see lambda greater than 1 is if you're trying to predict, say, house price using the Zillow data. One of your input variables might be the number of bedrooms. So the coefficient on the number of bedrooms in a house when predicting house price is probably pretty high in the thousands. So that would bring lambda down pretty quickly. But by comparison, if you're looking at square footage of a house, which is also usually in the thousands, then maybe the corresponding lambda wouldn't be so big.
But you're not picking a different lambda value for each coefficient, are you?
No, you're not. So it depends on the sum of the squared lambda values, but having a good idea of where this is going to be will help you tune your model.
Okay.
Other questions? Okay. So the basic procedure that we follow with ridge regression is like any other optimization problem. We set up a tuning grid, so we set up a choice of lambdas to try, either algorithmically or manually. We fit those different values using the training data, select the one that optimizes whatever our evaluation metric is going to be. Mean square error, mean absolute error, r squared. Then we'll apply that ridge regression model with the best lambda to the testing data, see how well it works. It's choosing these starting values of lambda that can be tricky. So here's a couple questions that I want you to consider. First, take a look at this sum here. This index starts at 1 intentionally. The intercept term in a regression model, beta 0, is left out of this ridge process. We don't penalize the intercept term. Why? What do you think is going to happen as lambda gets very small, approaches 0? What do you think is going to happen as lambda gets very big, approaches infinity? Take a few minutes to discuss at your tables, and then we'll take a look at some answers.
The sum of the square coefficients. Basically just saying.
It would consider that to be
It's going to take away the penalization.
So
It's minimizing the variance,
that's what happens as you go
and where the intercept is doesn't affect the variance. Because there's
Or you'll just have to
we didn't predict the intercept, and that's why it was
because when you have the plus
Yeah.
It's not
basically the size of
For her, I mean,
versus how much we have forcing. And so the higher your one, the more you're forcing it to 0.
So let's talk about these 3 questions. Question 1, why do you think the intercept coefficient beta 0 is not included in this summation? That intercept coefficient has a different interpretation than the rest of the coefficients. The intercept represents the predicted value when all of the other inputs are at 0. So it wouldn't really make sense to restrict that predicted value, since what we're trying to do is optimize the predictions overall. What happens as lambda gets very small? Well, looking at this optimization, as lambda approaches 0, the second term in the ridge optimization function will drop out. So we'll go back to least squares regression when lambda is 0. When lambda gets very big, all of the coefficients get forced to 0. So this is a hypothetical example using that MT cars data set. So built-in data set in R looking at cars from Motor Trend in the 1950s. What you're seeing here is what happens to the values of these coefficients for predicting mileage of a car as we increase the lambda coefficient. Here we're using the log because those lambdas can be pretty small. So with log lambda being a very big negative, that corresponds to lambda roughly around 0, we have the least squares coefficients. As we increase lambda, we shrink all of those coefficients down to 0. So all of these curves represent what's happening to the betas or the coefficients on these variables. Yeah.
Do you know or remember which log lambda was optimal?
For this data set, no.
Okay,
No.
just curious.
So could one like strategy to play with this to figure out what value of lambda causes your coefficients to basically get to be almost 0, and then use that as kind of a pseudo bound, like a pseudo upper bound for what you think you should be using for the greater value of lambda?
So figure out where you hit approximately this point where everything converges to 0 and
Yeah.
use that as an upper bound. You
Yeah.
certainly could do that. In the past, I've usually done trial and error, honestly.
Okay. Well, because like for instance, like when we try to choose, the upper bound for k,
Mhm.
right? We know what our upper bound for k should be kind of intuitively
Mm-hmm.
based on the data set itself, right? And so that's, I guess I'm trying to equate this to that a little bit.
Yeah, so what I would do in practice for figuring out what that lambda is going to be is start with a fairly wide net, so maybe lambda of 0.5, 1, 2, 5, something like that. Fit each of those. See if I'm getting that optimization shape in my plot of the model. If not, or where it looks like the peak is, narrow down lambda, try again. There are functions that automate doing this. Unfortunately, caret is not one of them. So we do some tuning by hand. So there are trade-offs with ridge regression. There are also advantages. So the big advantage here has to do with that bias variance trade-off. We've sacrificed some bias in our parameter estimates, but oftentimes this reduces the variance pretty significantly. So if the least squares estimates have pretty high variance, then ridge regression is a pretty good candidate. Ridge regression also has some computational advantages over other variable selection algorithms. So things like forward selection or backward selection, if you've used those before, take a long time to iterate through all of the possible variables to include in a model. This doesn't. So the selection that occurs is shrinking those coefficients to near 0. There are some disadvantages, and the big one with ridge regression is that all p of the input variables will stay in the model. So we'll get those coefficients, those beta hats, using a subscript r to indicate ridge. They will get close to 0, but they will never attain 0 exactly. So that means that the variables are still being included in the model, just at very, 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 very small coefficients. Prediction doesn't really bother things, but interpretation gets really difficult. So an alternative regularization model that does allow those coefficients to get to 0 is something called lasso regression. Again, lasso regression is estimating those regression coefficients with some restriction. The restriction comes on the sum of the absolute value of the coefficients rather than the squared coefficients. The name lasso comes from two different places. It's kind of a back-solved algorithm, or a back-solved acronym, excuse me. Least absolute shrinkage and selection operator. least because we're minimizing, absolute because we're using the absolute value, shrinkage because it's a shrinkage method, selection because it allows you to do selection, and operator to get an O in there.
Somebody's name.
It also comes from the old rodeo sport, lassoing. We're trying to rope our coefficients in, essentially, when we do lasso regression. The authors of your textbook are actually some, not all of them. Hastie and Tibshirani were the original inventors of the lasso and the ridge technique. They like to name things in silly ways. So that's where lasso comes from.
It's the only fun you get to have in stats.
There's actually a song about Robert Tibshirani out there.
Oh god.
10 points to whoever finds it for Gryffindor. Okay. So lasso regression, again, minimizes the following. The restriction has to do with the sum of the absolute values of the betas rather than the sum of the absolute value, or the sum of the betas squared. So we're not putting as big of a penalty here on large coefficients when we use lasso regression. This does allow those coefficient estimates to hit 0, unlike ridge regression. So what that means for us is that lasso regression ends up producing sparse models. We start dropping variables from the model once their coefficients hit 0. The procedure, exactly the same. We'll iterate through different values of lambda on the training data, try to optimize that evaluation metric on the training data, and then apply the lasso regression model with the best lambda to the testing data. So here's really a good visualization of the difference between these two methods. So picture, if you will, a 2-parameter regression problem. So we've got beta 1, beta 2. Beta 1 on the x-axis, beta 2 on the y-axis. What lasso and ridge regression do is restrict the space of possible solutions to be less than some criterion. So we're restricting in lasso regression the sum of the absolute values to be less than something. In ridge, we're restricting the sum of the squared coefficients to be less than something. So then say the least squares optimal beta is right here at the center of the contour plot. We're going to find the lowest value on the contour plot, so the minimum sum of squares, where that touches either the lasso diamond or the ridge curve. That's the idea. Yeah.
Why does it always touch the boundary at the top? Does that even make sense? Why?
It doesn't have to. It's just how this diagram's drawn. So the question is, why does it always touch at the top? It doesn't have to. The beta could be here. The diagram could be drawn down here. There's no reason. Yeah.
And just to clarify, so the value that we're now picking as our coefficient is the spot where that touches.
Yes. The values that we would pick for our coefficients are the spot where this contour first touches either the diamond or the circle.
And that's like minimizing variance and bias there as much as possible, I guess.
So we're sacrificing bias to minimize variance.
So it's like kind of like you're making the best model in between both, I guess.
Yeah. Other questions?
The red circles, what are, am I missing something? What are those?
So the red circles are contour plots of the residual sum of squares. So every boundary or every point on this line represents a set of parameter estimates with the same RSS. The farther we get from that point, the bigger that RSS is. The first point where it touches the diamond or the circle is the minimum RSS, minimum residual sum of squares, that meets the constraint. If you've ever used Lagrange multipliers in calculus to minimize a function, this is where they're useful.
So, in terms of bias and variance, or would we call their shape the exact rule variance, and then the distance away is the bias? Does that even make sense? Is that something?
It does make sense. It's not a term that I've heard in practice, but it is sort of but it does make sense.
Okay.
So the bias, for those of you watching at home, the bias would be effectively this distance between the least squares optimal estimator and where we're satisfying that criterion.
And that in effect becomes like a systematic bias of the way we're building the model.
Yep, absolutely. It's a bias that's baked into our model.
But nobody ever looks at this and talks about it that way?
No.
Okay.
Because you're using this to optimize your predictions, so you don't really care
Okay.
about doing the
As
inference.
long as it's predicting properly, you don't really care if there's some sort of systematic bias that would cause inference to be bad.
Absolutely. Yep. So one thing that is important whenever you're doing regularization methods like Ridge or Lasso is to pre-process your data. We've seen this happen in other situations too. K-nearest neighbors, for example, is very sensitive to the magnitude of the input variables. If they're not all on the same scale, the distances won't be comparable. The same thing with Ridge and Lasso. If we're going to shrink those coefficients, it would be really good if those coefficients were all on a comparable scale. So if all the variables that we're inputting into the model are on the same scale. So our solution is to pre-process the data. We'll transform the input variables to all be on the same scale, and then we'll fit the model to make sure that variables with different magnitudes aren't affecting how we're fitting the model. So one option here is to use a z-score to standardize the variables. So here we'll take each input. So x input sub ij, variable j, observation I. We'll take that input, subtract the mean for variable j, divide by the standard deviation for variable j, effectively return a set of variables all with mean 0, standard deviation 1. So this would force all of the input variables to be on the same scale. The way that we can accomplish this, so here is our air quality UCI data set. We can do this by using a function in here called pre-process. Method equals center says to take all of those variables, shift the center to be 0, so make all of them have mean 0. Scale says to make all of them have standard deviation 1. So applying this would force all of them to be of the same center and scale. Effectively, what we do when we use this pre-process function is create a recipe or create a list of steps for doing the pre-processing. Jake?
Could you do the same thing but just with some columns of the data set and then just replace some of the columns if you don't want to replace the whole thing with standardization?
You could absolutely do this manually. You could replace some of the columns. I would recommend against processing only some of the variables because you're introducing bias then when you do that. So if you're going to process all of them. So what is created by this is, again, a list of how to process. So these are the processing instructions. This hasn't actually processed the data yet. In order to apply it, we predict using this pre-process. So here I've got my training data and my testing data that I had already defined. I'll then predict using this pre-process function to create a transformed training data set and a transformed testing data set. Always do this on both. It can be more efficient to predict or pre-process the entire data set before you split. That's fine too. There is another commonly used method here to bound everything from 0 to 1. So if you pre-process using range bounds, you can set your variables to be between a certain minimum and maximum.
So that doesn't result in a z-score.
No, so this doesn't result in a z-score. This represents in scaling all of the variables to be bounded so that the minimum is 0, maximum is 1.
Where Are you gonna get into where you think that that would be a good idea versus like doing like a scale and center?
Both tend to work reasonably well. A reason why you might choose one over the other is if, for example, there's some skew in the variables and you want to preserve that skew. Another reason why you might want to do something like this is if the quantiles or the percentiles of the data have a nice interpretation or make sense to work with, then you might do this, which effectively transforms to percentiles. Other questions? Jake,
Does it ignore or throw errors at non-numerical variables?
let's see. So here is what we've done. So here I'm using head to just show the first three. When I process this data, I left date and time in here. Those we know to be categorical factors. Before date and time looked like it was all around March 10th, 2004. It still looks like it's around March 10th, 2004. So Caret will automatically recognize that those categorical variables don't really make sense to calculate z-scores on. And even if you leave them in there, it won't do it. If we wanted to make sure that those aren't in there, we could always remove those columns in our pre-processing recipe like this. But for the most case, Caret is written to recognize those categorical variables and not transform. Yeah.
So are you just replacing the old variables with the z-score for it?
Yes, so once you predict using this pre-process recipe, all of these variables here in the transform data have been replaced with z-scores. Yep. Yeah.
So I guess I don't understand like the 0 to 1 bounds very well. So like with this, I'm assuming you're just getting the z-score so you can compare everything.
Mm-hmm.
But with the 0 to 1, like what are the values being set to?
So the 0 to 1 is going to take the minimum value of each of the input variables and shift that to 0. So to get the 0, 1 bounds, we'll take the x, we'll subtract the minimum, so that's going to force the minimum to be 0. We'll divide by the maximum minus the minimum. So
Okay.
that will force the upper bound to be 1.
Okay.
Everything else will be somewhere in between.
Okay, that makes sense.
Other questions? Okay. So in general, the workflow here, define how you want to pre-process the data first. Either pre-process first and then create your split, or create the split and then apply pre-processing. Either one is fine. Here I chose to apply the split second because I had already created my training and testing data. Yeah.
Do you have a preference, like at production scale, about whether you would want to store 2 sets of your data set as like untransformed and transformed, or just transform the original and risk losing possibly the original values, or having to read that all back in at some later date?
So at the production scale, I would do the processing within the model fit step, which we'll talk about how to do a little bit later.
Okay.
Because that then saves having to create more data storage. Okay, so ridge regression and lasso regression are actually special cases of a technique known as the elastic net. So the method that's going to implement all of these is method GLIMNet, GLM for generalized linear model, net for elastic net. There are 2 parameters here, and I claim the following. I claim that alpha equals 1, and the elastic net penalty is the ridge penalty. alpha equals 0 in elastic net is the lasso penalty. So here is what that elastic net penalty actually looks like. We take that lambda and we pull it outside of a weighted sum. So we are adding some weight applied to the sum used in ridge regression plus some weight applied to the sum used in lasso regression. So if, for example, we set that alpha equal to 1. Oh, I have those switched. Sorry about that. Alpha 1 is going to be lasso. Because if alpha equals 1, our penalty becomes 1 minus 1 over 2 times the sum of the squares plus 1 times the sum of the absolute betas so alpha equals 1 will implement lasso regression. What about alpha equals 0?
Back to our least squares.
Alpha equals 0. We're not back to our least squares.
Lambda's 1.
Oh, I'm looking at lambda.
We get this. But since that lambda is an arbitrary constant anyway, alpha 0 is ridge regression. So alpha anywhere in between is going to be some combination of lasso and ridge. So our lasso penalty in two-dimensional space is a diamond. Our ridge penalty in two-dimensional space is a circle, so that elastic net penalty is going to draw a boundary somewhere in between. It's pretty cool stuff. So, how do we, Shelby, yes?
So if you said alpha equals 0 is ridge, if alpha equals 1 is lasso, or is it anything that's not 0 is a combination of both?
Anything that is not 0 is a weighted combination of both. So alpha between 0 and 1 is something that's not quite ridge and not quite regression. So here's how you might implement this. I'm going to set up a grid of tuning parameters here. So I'm going to let alpha be a sequence from 0 to 1. And here I'm just going to go in increments of 0.1. So 0, 0.1, 0.2, and so on. Lambda, I'm going to go from 0 to 3. Again, I'm going to choose a grid length of 11 here, just so I have nice decimals with this. And then my grid of tuning parameters is going to be every combination of these. So there's 121 different combinations of tuning parameters that we're going to test with this first fit of the model. So we'll fit the model using method equals glimnet. We're using train transformed, so this is the pre-processed data. Our tuning grid has 121 combinations, so this is going to scroll down pretty far. We'll go ahead and fit this so we can take a look at it in live code. 121 combinations for the tuning parameter sounds like it might take a while. Don't think it does. Everything before. While this is going, one thing that I do want to remind you guys of, as you're writing your homework, if you're using RStudio, every time you rerun code, even if you're just playing around with it, when you set a seed, you're still moving farther down that seed. So your seed value might not return necessarily the same thing. Did we do that?
So if you want to see it live, the same way that you would see it when you knit, you have to run it from the beginning every single time.
You have to run it from the beginning every single time if you want to see it live as you knit. What I typically will do is actually have it knit over here in my viewer pane and then refer back to that. One other solution that you can do, you can actually call live code in the text area. So if I write R 2 plus 2 and knit this, what you're going to see in the notes when they pop back up in a few minutes is 4 in that space. So that code's going to be executed in line rather than in chunk. Two plus 2, 4. So that's another way that you could reference output and have it change dynamically. Okay, so here are the results of the 121 different runs. If we look at R squared, it's still pretty high, mean absolute error. We want to try to find the optimal R squared. At some points, we are going to get not a number pop up. This isn't necessarily a bad thing. We'll talk about why this is popping up. Looking through this table isn't ideal. So we might create a plot of all of the different parameters. This mixing percentage down here, this is the alpha. We're looking for optimal R squared, and simple models might be better. So optimal R squared seems to happen at regularization parameter 0.9, has the highest curve out of all of these. It looks like mixing percentage somewhere between 0.2 and 0.4 is pretty good. So I might narrow in on that set of combinations the next time I fit this to try to improve.
What makes the 0.2 to 0.4 range better than like 0.4 and 0.6? Or like
So we might look in here too. So 0.2 to 0.6, somewhere in here looks like it's going to have the optimal.
So are you looking for them to all be different? Or what
We're looking for the highest. Oh no, sorry, we're looking for lowest mean square error. My apologies. I'm used to looking for K's. Lowest mean square error, where is that going to happen?
0.2, 0.2, or it's either 0 or 2.1. It's kind of hard to tell.
Either 0 or 2.1, so we could look back at the output. This is unfortunately one of the downsides of these plots is that they're created using the base R color sequencing, which is repeating after a while. So somewhere in here is going to have the lowest mean square error. Again, apologies for that. Yeah.
In either case, the blue one appears to be
This looks pretty good.
right, but either blue one is changing as the mixing percentages changes. Why would that happen when the regularization parameter is 0? Wouldn't that mean that neither lambda is having any impact?
So if the regularization parameter is 0, then that means that we're fitting ridge regression. So over here, we've got ridge. Over here, we've got lasso. This is our in-between with ridge and
Right,
lasso.
for the alpha, but is the regularization parameter alpha or is that lambda?
Oh, regularization parameter, this is lambda.
Right, so when lambda equals 0, why does changing the mixing percentage change even for that bottom blue line, which I'm assuming would be 0? Why is it a little bit different from 0 to 0.2, like as alpha changes? Shouldn't it all be the same? Shouldn't it be RSS either way?
So remember, we're bootstrapping as we fit this too.
Okay.
So that's where the additional variability is going to come from. Other questions? So again, we can look at these plots. From this, Intuition again tells me that usually these lambdas are pretty small. So what I might do is decide to fit a new lambda grid, maybe from lambda 0 to lambda 0.3, maybe mixing percentage somewhat high, and refit the model. Those NAs, I did a little bit of digging because those happened fairly frequently for me. And this is the response that came directly from the Carrot developer. So what's happening here is you have one hidden unit in the model, so one variable in there that so that hidden unit, that is, what was that? I'll have to look back and see what that was. But almost no regularization. So almost no regularization, mixing percentage, or sorry, regularization parameters, these are very low where that's happening. So what is happening here is that the model's predicting very close to a constant, so there's not a lot of variation here. The root mean square error is actually a little worse than the basic standard deviation. When error estimates are worse than the overall error, those get forced down to 0. And so we're really not explaining much variability, and that's why we get back not a number. To get maybe a better idea of how this works than just those straight line plots, I did a contour plot instead. So here we're looking at where this root mean square error is minimized. The darkest blues are right along here, so at the very small lambdas. Yeah.
So if you have like is the goal to minimize it with being as far away from 0, 0 as possible?
So root mean square error will always be a little bit bigger than 0. The smaller we can get that, the better.
I mean, like the tuning parameters. So like because like here it looks like the alpha and the lambda at both set to 0 is like optimal. But what if we could push that to be like, 1 and 1/4? Like, would that be better for like bias concerns?
If we have those bias concerns, then yes, we might want to choose a lower lambda or a lower level of bias. Again, most of the time in machine learning, from that perspective, we're really focused on the prediction side of the problem. And from the prediction side of the problem, bias isn't an issue. So what we might do is look at a finer grid. So I reduced my lambda down to 1, did a 20 by 20 grid, took about 21 seconds, so not too long. I also changed the color from the default ggplot just so we could see those differentiations between small and very small. So we want small root mean square error, we want blue. It looks like, again, the smaller the lambda is, the better. We might keep zooming in, which I did. Smaller is better. Looks like maybe this alpha 0.5 is getting pretty good. Lambda 0.01. How do we know when to stop?
When we go pretty good.
You're satisfied? We never
When our model predicts well?
Whatever makes you happy.
We don't know. There's no good stopping criteria for a process like this. So when do we stop? That's a wonderful question that I can't answer. Yeah.
Well, so is a lambda of 0 still having an impact on the predictions? Is it like, so then there's no penalty when you're calculating?
So lambda equals 0 drops the penalty. Lambda equals 0 is least squares regression.
Yes, it's no regression.
Yep.
Okay.
Okay, so we'll give it one more go for S's and G's. So here's my 100 by 100 grid on that region. I took lambda to be really small here. So from 0 to 0.05, this took about 4 minutes. optimal lambda and alpha combination is going to be somewhere in here. All right, so we will stop here because that's kind of a good stopping point for the midterm. We'll talk about principal components regression after the midterm. What I'd like to do instead for the rest of the time is start a little bit of review. So like with our, actually we haven't done the cards in here. We've done them in other classes. So each of you is getting a card with a number on it. So in the groups that are on your number, I'd like you to take a look at your notes over a specific section. So there are 2 jokers out there. So 2 jokers. Pick a 2 or a 4. 2. So your task is to go through the section and complete the following. Write 3 or 4 review questions over your topic that you can confidently answer and the answer to those questions. I'd also like you to write 2 or 3 that you can't confidently answer and would like more clarification on. Dang, sticky keys showed up again. I have a sticky L and a sticky H, so I apologize if you see those pop up. There's the L.
Which mean you apologize.
Ha ha ha.
There's no test here.
So, you've got about 20 minutes to complete this. You can either write your answers on a sheet of paper or type them up and email them. I'm going to compile the lists that you guys create and disseminate them out. So you'll have the review questions from all of the groups. I'll also fill in some answers for those questions that you can't confidently address.
5,
There's no sound.
7,
3,
2.
Go.
2.
is there
Winner's quarters?
oh what's